In Chapter 13, we're going to look at chemical kinetics, and this is the speed that our chemical reactions take place at. This is very important because if reactions occur too quickly, they can be dangerous and explosive. If they occur too slowly, they may not be useful for our application. And so being able to control the speed and look at the speed of these chemical reactions is essential. As always, there's a few suggested problems for you to try at the end of the chapter. We need a way in order to measure the speed of our chemical reactions. And so one way that we measure it is through the rate. And a rate is just a quantity that changes over a given period of time. So we're pretty familiar with this in our everyday life. So if you're driving a car, the rate that you're driving the car is miles per hour. It's the distance that you travel divided by a certain amount of time, so miles in 1 hour. And our units are miles per hour, so the distance divided by the change in time. Or you can think about things like weight loss, so pounds per week. So it's always some quantity divided by time. For talking about chemical reactions, we're going to have to use units that make sense for chemical reactions. So we measured the quantity as a concentration of our reactants. And if we're looking at reactants, that quantity is going to decrease. So as the reactants get used up, their concentration decreases over a certain amount of time. If we're looking at the products, then our concentration increases over a given period of time. And so we represent this as a negative sign when we're talking about reactants, showing our decrease in our concentration. So our concentration is typically measured in molarity. We take the molarity of our reactant, final molarity of our reactant minus the initial molarity of our reactant, and divide by the time point at which those molarities are measured. So we do have a delta, so it's change in concentration, and the brackets around mean concentration. So whenever you see the square brackets, think concentration. When looking at a chemical reaction, and our example reaction that we're going to look at is hydrogen plus iodine forming hydrogen iodide. And we can look at how that concentration changes over time. So as our reactants get used up, our concentration is going to decrease over time. As our products are made, the concentration is going to increase over time. And if we want to calculate the rate, we can pick 2 points along our graph in order to do our calculation. Now, we can pick any 2 points. However, the closer our points are to each other, the more accurate our estimation of the rate at that time is going to be. So we're doing a linear approximation of our curve. As we decrease the distance between the points on the curve, our rate gets even more accurate. Up until the point where we're actually taking an estimation at 1 point. So we're drawing a line that is a tangent to the curve at that point, and this is called the instantaneous rate. And it's the change in concentration at one particular time. We're taking the slope at 1 point of the curve, and this is what we call the instantaneous rate. And for those of you that are calculus fans, this would be the first derivative of the function. So average rate is taking it at any 2 points along the curve, and instantaneous rate is taking it just at 1 point. The change in our concentration divided by our change in time. Now, as you may have noticed, that our curve starts to flatten out as time goes by. And the reason for this is because it's slowing down because the concentration of our reactants is decreasing. As they get used up, it's harder and harder for the molecules to find each other to react. At some point, that reaction is going to stop, either because the reactants completely run out or we've reached equilibrium.